What's up, guys? Today I'm doing a video on factoring, and this is an extremely important topic in this class and any math class you go on to after this. Now, you've done some factoring before, but I can't be too sure what you've got and what you don't have. All I do know is that in this class, you're going to use factoring in virtually every unit that we cover, and it's extremely important before we move forward that you've got at least these four basic types of factoring mastered before we go any further. Okay, now this is really just scratching the surface of factoring. There's a lot more factoring types than this, and quite honestly, we should probably be covering more than just this, but we feel like it's so important that you understand these basic four types that this is really the only thing we're going to focus on for now. Okay, and later in the year when it comes up, we may move into some other types of factoring like sum of cubes and differences of cubes. But for now, we're just going to focus on these four. And if I can get everybody to master these four, I will be very happy. Okay. So first of all, we need to make sure we understand what factoring is. Factoring is just when you write some polynomial as a product of two or more factors. And you can see the definition in my notes. Go to my website, look at the notes. I'm not interested in going through definitions here. I want to show you how to do the process. Okay. So there's the four types of factoring, and kind of written in the order of difficulty, I would say. GCF, of course, stands for greatest common factor, and it's really not the kind of factoring you're going to use most of the time. But there are times where the only thing you can do is pull out a GCF. All right, so for example, let's do an example of GCF factoring. So maybe you have something like this. Okay, so here's a problem where we can factor, okay, there is a GCF we can pull out. And I would always say, if there's a GCF you can pull out, you should always pull it out no matter what. Even if you're going to go on to do other things, we should always look for that GCF that we can pull out, okay? So what's something that I can divide both terms by? I can divide both of them by a 2, and I can also divide both of them by an x. And so I'm going to pull out a 2x from each term. Okay, it's like the opposite of distributing. I'm undistributing. I'm dividing a 2x from each term. All right, if I pull out a 2 and an x from this, what would be left is another 2x. And if I pull out a 2x here, that would leave a 1. So again, remember, if I were to distribute these, if I were to say 2x times 2x, I'd get 4x squared. And if I said 2x times 1, I would get 2x. Now in this case, that's all I can do. Now you could, some people will say factor completely. Completely factoring in this case would actually mean you want to highlight the fact that 2 and x are two different factors. So you might be, there might be somebody more nitpicky than me that would actually rather you say this and explicitly write out every single factor as completely factored down as possible. Okay, that would be another way to write it, but I'm in this case generally okay with this. Okay, for our purposes, this is going to do what we need. Including in the units that we're coming up to later. Okay, so that's GCF factoring. That should be a basic skill at this point. We're just factoring out whatever the greatest common factor is for each term. Okay, then you have problems like a difference of squares. Okay, a difference of squares is exactly what it says it is. Okay, it's one of these things where the name specifically describes what's going on. It's a difference, which means we're subtracting something from something else. That's what difference means. So we're subtracting two things, and the things that we're subtracting are squares. So literally they're perfect squares. So maybe I've got, we could say 25x squared. That's a perfect square. And I'm going to subtract from that another perfect square, so maybe 9. 25x squared is a perfect square, and so is 9, and there's a subtraction sign in the middle. So again, if the instructions are to factor, and I look at it and I see it's only got two terms, and both of those terms are perfect squares, I'm going to use the difference of squares method. Now, number one, this had two terms, right? But there's some problems. 4x squared is a perfect square, but 2x is not a perfect square. That's the first problem. The other problem is that in the middle, there's a plus sign instead of a minus sign. So you're not going to use the difference of squares here. But if I see two terms, both terms are perfect squares, and there's a subtraction sign in the middle, it's a pretty strong indication that I need to use a difference of squares to factor this, okay? In fact, there's not even a GCF you could pull out on this one if you wanted to. Okay, so what is the square root of 25x squared? It's 5x. So I'm going to write whatever the square root of this is. I'm going to write that here. And what's the square root of 9? That's 3, right? I'm going to put that here. And so I've got 5x plus 3 times 5x minus 3. And that's how you factor a difference of squares. It's the product of one square root plus the other and one square root minus the other. Okay? If you think back to when we were multiplying our complex numbers before, these are actually what we call conjugates. Now, these are not complex conjugates because there's no I involved. These are just regular conjugates. And just like with complex conjugates, there's a rule for that. When you multiply conjugates, so if you have a plus b and a minus b, notice there's no I this time, that's going to give me a squared minus b squared. Now remember when we had an I in there, we said a squared plus b squared. Well, there's no I, so there's nothing to change that sign. So it's the difference of those two squares. So actually what we have here is multiplying conjugates in reverse. If I were to start with this, and if I were to multiply these together, your middle term would cancel out when you did the box, and you would end up getting this difference of squares. These are conjugates, and they multiply to give you a difference of squares. That means we can work the other direction and say, well, if I've got a difference of squares and I want to factor that, then I can just write it as these conjugates. The square root of each term, and you say one plus the other and one minus the other. All right, so this brings us to monic quadratics. Monic quadratics are also very easy. This is probably a type of factoring that you've done many times before, but it's where a is 1. And when I say a, I mean when you've got a standard form quadratic. So if you've got ax squared plus bx plus c, which you should remember from last year, a, b, and c are the coefficients, sort of. So that leading coefficient, a, if that is 1, like it is in this problem, then that's what we call a monic quadratic, and it means that factoring is very simple if it's factorable, okay? So all we have to do is say, what are two numbers that multiply to make 6 and add up to make 5? They need to multiply to make c and add up to make b. Those two numbers would be 2 and 3. And then I write it this way. I just say x plus 2 and x plus 3. Okay? These two numbers multiply to make 6 and they add up to make 5. Okay? If I were to use the box and multiply these out, I would get back what I started with. Okay? Now, number 4, even though it's not a monic quadratic as it's written right now, we're going to treat this one like a monic quadratic. And the reason is, when you look at it, say, okay, is a 1? No, it's not. But the next question you ask is, can I make a equal 1? In other words, can I factor out whatever a is? And in this case, I can't. You should always check for a GCF first. And I can divide all of this by 2 first before we even get started. So I'm going to factor out. I'm not really going to divide it out. I'm going to factor it out, meaning it's still there. I just pull it out to the side. And that's going to leave x squared plus 4x plus 4. Okay, now remember, if I were to distribute that 2, I get right back to what I started with. Okay, so I haven't really changed anything. I'm just sort of rewriting it by factoring that 2 out. Now what I've got left is a monic quadratic, and it's one that I can factor. Two numbers that multiply to make 4, that add up to make 4, that would be 2, right? So I can rewrite this one as 2 times. Always remember that your 2 is still out there. Do not forget that GCF. Sometimes people get so wrapped up with this part and factoring it that they forget that that GCF is still there, and then they don't write it in their final answer. You need to remember that that is there. All right, so two numbers that multiply to make 4 and add up to make 4, that's 2 and 2. So I'm going to say x plus 2 and x plus 2. And this is the answer. If you write x plus 2, and you didn't put the 2 on the outside over here, that's going to be wrong. You need to remember that that's still part of your factors. Okay, now this particular problem, because these are the same thing, you could also write this way, and I have no real preference, although it's probably better to just leave it factored out as far as possible, but you could write it this way as well. Okay, so now that brings us down to non-monic quadratics. Okay, now this is the hardest type of factoring that I'm going to ask you to do this year. Okay, it's far from the hardest type of factoring you'll ever do, and in your senior year, you will definitely be dealing with sums and differences of cubes and all types of other stuff. But this is the most I'm going to ask you to do, okay? A non-monic quadratic is when a is not 1, okay? Leading coefficient is not 1, and you can't make it 1 by factoring out a GCF, Okay. So the first problem we're going to look at, 6x squared plus x minus 12. Okay, again, there's a 6 out front. Can I divide everything by 6? Well, I can divide this by 6, but I can't divide that middle term by 6. So I can't factor out that GCF. I can't make it go away. Okay? So what we have to do on a non-monic quadratic is, instead of looking at b and c like we did up here, we only looked at the 6 and the 5, for example. We didn't pay attention to the a because a was just 1. Well, in this case, we can't ignore a. So I need two numbers that multiply to make a times c that add up to make b. And I always just call them m and n. I've seen it written that way a lot. So I tend to call these two numbers m and n. What is a times c? What's a times c in this case? 6 times negative 12. That's negative 72. And b in this case is 1. So what I need to do is I need to think of two numbers that multiply to make negative 72 that add up to make 1. I find that a lot of times it helps to go off to the side somewhere and just write out what pairs of numbers multiply to make 72. And we can worry about the sign later. Let's just get the numbers first. Well, there's 1 and 72. Can I add or subtract those in any way to make 1? No. There's 2 and 36. That's not going to make 1, right? There is 3 and 24. That's not going to work. 4 and 18. That's not going to work. 5 doesn't go in. 6 and 12. Still doesn't make 1. 7 won't go in. What about 8 times 9? 8 times 9 is 72. Okay? Those look like they could make a 1, right? But we got to get the signs right. Okay, so a times c is negative 72. That means if we're using the 8 and the 9, one of them's got to be positive and one of them's got to be negative. But when I add them together, I got to get a positive 1. So that means the 9 must be bigger, or the 9 must be positive, sorry. We know they're different signs, so negative 8 and positive 9. Let's try this, okay? They're both, one's negative, one's positive, so when I multiply them together, I'm going to get negative 72. When I add those together, I'm going to get positive 1. Here's what the signs tell you, okay? If you have a negative sign for a times c, that means the signs are different. So then you look at the sign of b, and that tells you what the bigger number must be. Since b is positive, if I'm adding together some negative amount and some positive amount, and I've got a positive left over, then that means the bigger number must have been positive, okay? So negative sign here on a times c, that tells me the signs are different. The 1 here tells me that the 9 must be the positive number. If this had been a negative 1 right here, then we'd have to flip the signs. The 8 must have been the positive number. The 9 must have been negative. The bigger number must have been negative in that case. All right, so what do? This is where it gets different, really. Yes, we had to multiply a times c, but the bigger difference comes in what you do with those two numbers. A common misconception is that people want to do what they did on monic quadratics, and they just want to say x minus 8 and x plus 9 and call it a day. If you just said x minus 8 times x plus 9, just to show you why this is not the answer, look what would happen. Now, if I were to multiply these together, look at the very first term. X times x is x squared, not 6x squared. So you know that regardless of whatever else happens, you're not going to get the right starting term, so this can't be the right way to do it, okay? So with a non-monic quadratic, you got to do something different with these, okay? And I'm going to show you a little bit extra steps here versus what I would normally do, just to make sure we understand. But I'm going to rewrite the original quadratic, 6x squared, except for this middle term. Instead of saying 1x, that is a 1x right there, right? Instead, I'm going to say minus 8x plus 9x, and then I'm going to write my negative 12 at the end. So I replaced this. Remember, that's just 1x, right? We know that these add up to make 1x because that's part of the reason why I picked these numbers. I knew they would add up to make b, which means I can rewrite bx as mx plus nx, okay? So I've simply rewritten, I kind of split that x into a negative 8x and a positive 9x. I'm allowed to do that, right? Now what I want to do is, and I've seen a lot of different ways to do this, and if you read my notes on the website, there's a slightly different method given, okay? But over the years, I've kind of decided I like this other method a little better, and it's really the same thing, but it comes back to using a graphic organizer to make it easier to understand and follow. And so that graphic organizer is the box. That same box we used when we were multiplying, except we're going to use the box backwards, okay? So what I want to do is I want to take this polynomial that I've written out, and I'm just going to plug each term into the box. So I'm going to say 6x squared minus 8x plus 9x and minus 12. I've simply written those four in order, 1, 2, 3, 4, okay? Now remember that normally the way we use the box is you've got something written on the top and something written on the side that we multiply together to give us these numbers. Well, instead, we're working backwards to figure out what would have to go out here that would multiply to give me these numbers. Whatever's going to be out here, that would be the factors I'm looking for. Well, the easiest way to do this is I say start at the top row and pull out the greatest common factor of the top row. Now, it's very important that you pull out the GCF. I have teachers come to me sometimes and say, that box method seems to work, but sometimes it doesn't always work. The reason it doesn't always work is because you're not pulling out the GCF. You have to pull out the greatest common factor, okay? I can't just pull out a 2 on the top here, for example. If I do that, I'm going to get the wrong answer. You must pull out the greatest common factor. So what can I pull out of both terms? I can pull out a 2. I can also pull out an x. So 2x is the GCF for that top row. Now, if I pull the 2x out from each of these, what would that leave behind? That's going to go up here. If I divide 6 by 2, that's 3. And I pull 1x out, so that leaves an x. So you've got a 3x here. Now check, if I multiply those together, I should get 6x squared, and I do. And if I pull out a 2x here, that's going to leave me with a negative 4. And check, 2x times negative 4 is negative 8x, okay? Well, now we need to take these numbers down here and say, all right, well, if I pull a 3x out from 9x, what does that leave? 3. 3 times 3x is 9x, and check, 3 times negative 4 is negative 12. These are going to be my factors. 2x plus 3 and 3x minus 4. Okay, I'm going to do one more example of a non-monic quadratic. See, we're on number 6. 12x squared plus 5x minus 3. I'll try to go a little faster on this one. All right, I need to figure out a times c and b and m and n, because a is not 1. I can't make it 1 by factoring out a 12. So if this is factorable, this is going to be the way I have to do it. Okay. What is a times c? It's negative 36. What is b? That's 5. So I need two numbers that multiply to make negative 36 that add up to make 5. Okay. Those numbers are going to be 9 and 4, but I don't know about the signs. This tells me the signs have to be different. Okay. This tells me the bigger number must be positive. Okay. So since there's positive left over, the bigger number must be positive. That means the 4 must be negative. Always double check. Negative 4 times 9, that is negative 36. They do add up to make 5. Okay. So what I want to do is rewrite this 12x squared plus 9x minus 4x minus 3. I'm going to draw a box. And I'm just going to plug these in. What's the greatest common factor for the top row? I see a 3 and an x. And that leaves a 4x and a 3. Double check and make sure they multiply out the right way. And if I pull a 4x out from here, it just leaves a negative 1. And check, does negative 1 times 3 make negative 3? Yes. So everything lines up. If I multiply these together, I do get what's in the box. Okay. Therefore, my factors are 3x minus 1 and 4x plus 3. If you think about why this works for a minute, think about the steps here. All we did was we split that 5x into a 9x and negative 4x. That's equivalent, right? If I add those together, I get 5x. So I haven't really changed anything. And then what I did with the box was I figured out what numbers would go on the outside so that they would multiply together to give me the box. Well, what's in the box was that polynomial that we already had. So all we did was figure out what things we can multiply together to get this quadratic that we started with. And those things, those factors, are 3x minus 1 and 4x plus 3. And now it's factored.